It's part 2 of openDog version 2, but please watch part 1. I spent a long time making that video and there's a lot of information in it about where we are with the robot dog R&D and what the plan is, so it's really important to recap on that. I can't repeat it all again in this video, so it's really important to watch that video. I'll be using all of the previous robot dog R&D that I've carried out to build this version, so check out the miniDog version 2 to see a dog that walks. This is a really important R&D effort for dynamic walking, balancing on 2 legs as it goes. I also built some test legs and dogs last year which use brushless motors and low reduction gearboxes that can be back driven so that I can make simulated springs and make the legs comply with the ground based on IMU data or foot sensors. I'm going to be using all of that previous R&D in the new build, and today I'm going to be building one test leg with some joints to check out the core mechanisms, and I'm going to show you quite a lot of detail about the thought process and the design. So I'm going to be using 90 kV Turnigy 9225 drone motors for this build, so they have quite a large diameter which will give lots of torque due to the increased leverage. I'll be driving the joint through Quasi-Direct Drive, which means it's a low reduction and it can be back driven. This will allow us to use the same encoder that positions the motor to sense force on the joints, so check out the previous test dogs for more info on how the controller worked there. But before we get started, it's just a quick ad for ways you can support the channel, and that really makes all the difference to the projects. I have Patreon and YouTube channel membership, and patrons and YouTube channel members can get access to all the videos up to a week early, and also sneak peeks and pictures about what's coming up and be part of that discussion. There's some affiliate links in the description to this video, and if you sign up to one of those services, it won't cost you any more, but I'll get some money. And also have a merchandise store where I have various t-shirts, bags, socks, stickers and mugs with designs on including miniDog, openDog, and there'll be one for openDog version 2 once we know what it looks like. Right, let's have a look at the design. In the last video I spent quite a long time discussing how I'm going to lay out the robot, including the motor and pulley placements, but since then I've done quite a lot more detailed design. And that looks like this, so I've mainly concentrated on this upper hip design with one motor with a pulley driving a big pulley which drives the upper leg. So if I just remove that pulley, we can see that in fact it's on a square shaft made of 2020 extrusion, and that's seated in bearings on the front and the back, and there are some square bushings here which mean that that square shaft will fit in the bearings. There's also 2 idlers which will help tension that belt if I even need to tension it in the future, but for now I've made this assembly in 2 pieces so that I can reprint the smaller piece to get the belt tension right to start with, and I don't have to reprint the whole thing. So let's print these parts off and see how well that belt works and whether it slips or skips or whether it's nice and tight. So first of all, I trialled and errored the pulleys. I don't have a generator for these. I basically drew them manually, adjusting the tooth width and the number of teeth to get a 5:1 ratio. So that's 14 teeth versus 70 teeth. And the belts I'm using are HTD belts with a 5mm pitch. So in the end, the 70 tooth pulley worked out all right, and we can see that's nice and tight on there. There's no gaps, and there's lots and lots of teeth. So obviously it's quite a big diameter as well. So even though the belt's quite stiff, it's unlikely to skip on there. The one that concerns me is the small one, which has only got 14 teeth. And in order to get that belt on there tight, you know, we need to wrap it round quite tight, and then it's got less teeth to engage on, so that may be more of a problem. Obviously we don't want to pull it too tight because I don't want to wreck the bearings in the motor, which is a drone motor, but let's look at that next. So here's the motor, and the whole top of this turns. The bottom is bolted down and the top turns, so we've got these 4 holes here as well as the centre pin which all turn, so that's quite good for attaching things, and normally of course we'd attach a drone rotor. So the pulley was designed to fit on there and have 4 screw holes, and this still isn't the final one, so that gives us quite a lot of leverage. Obviously the drone rotor normally fits on, so the load on the motor is sort of up and down. With this we're going to be pulling it sideways, so I'm not sure how the bearings are going to stand up, but there's probably a solution for that which we'll discuss in a moment. So I went ahead and assembled it, and everything works out quite well. That belt's really quite tight. I did do one other trial piece of this, then I moved the screw holes so that we could get the motor tensioned perfectly, and we've still got those spaces for the idlers. So I've just propped this up on something. Obviously the axle goes all the way through to the bottom, but now we can just try tensioning this and seeing if we can make the belt skip on the smaller pulley. So even if I apply as much force as I can there. We can see the belt bulging slightly on that side or on the other side, but I don't think I can make that skip. And we do have the option to install idlers in here to pull the belt in even tighter, just by putting some M8 studding in there, which will actually be bolted on both sides, putting some bearings on, and then pulling that belt in. And we could just 3D print bigger barrels to put on here, which just pull that in by 1 or 2 millimeters on one side or the other, or both if we need, if the belt stretches. And that would still of course run perfectly well. My concern about putting tension on this pulley, of course the belt is pulling it towards the other pulley. We could fix that by making an extension on this pulley, fitting another bearing in, and having a parallel plate on the top which supports both of these and has another shaft holding it. So that would give some extra support for the motor bearings. So the next thing to do is check the holding power we can get out of this motor and this gear combination, but to do that we need to put an encoder on the back of the motor there onto that hex nut which is turning around. And the encoder we're going to use this time is the AMS AS5047, which is a magnetic encoder, so it comes with a little magnet in a bag, and that magnet has to float around above the chip and it rotates round, and that gives us absolute position and also AB phase, which we can plug into the ODrive. So that means we can position and control the motor with the ODrive and also read the data off to our own microcontroller to home the joints and things like that. So we're going to put a piece on the back that fits that hex nut. For now it's a push on and it's going to hold that magnet. Eventually we'll probably glue them on, and then behind that is going to be a piece attached to screw holes that I cunningly left, which is going to hold the actual encoder, and that's got a slight raised piece there so that we can get the distance just right, and there's somewhere for the solder terminals to go on the back side of the board. So I've got that piece there, it's all just push fit really with the magnet pushed in, and it push fits onto that hex nut, and that seems to rotate nicely in the centre. And we've got the mount here for the encoder. So of course the encoder board fits onto this plate. I haven't screwed it on yet, but it fits just there. The only thing that's a bit silly about this evaluation board for the encoder is this massive jumper right in the middle of the board, and that's for 5 volt or 3.3 volt select for the voltage for operation. So I'm probably going to have to cut that off. Even if I pull off the actual jumper on top, there's still some massive pins sticking up, and that makes it really hard to get the magnet close to the chip. So I've attached that to my board here with some screws that are a bit oversized, but that's all I've got. I've got the header pin here. This is a header strip it comes with, and I've attached the wires here for the A and B phase and ground and 3.3 volts. And that's because the ODrive is a 3.3 volt device. And in order to make that work, I had to bridge out the jumper, which I've now cut off, to 3.3 volts. And according to the datasheet, also move a 0 ohm resistor from one spot to another, which of course I haven't done. I've just pulled the original off and put a solder bridge in. So I left the screw holes in this plate to attach the encoder, so here it is, and that will just fit on the back there and screw down, and that should be exactly the right spacing for that magnet and encoder. So here's my little test setup. We've got the motor and the belt reduction, of course, with the encoder attached, and we're using an ODrive to control it. Now this is an ODrive 3.5, it's the 48 volt version. It's one I took out of the original openDog, which I'll be using in this build. It's not the latest version, but it's perfectly good. I've had to change some parameters using the ODrive tool. Mainly the pole pairs for this motor is much higher than most other motors, so there's 20 pole pairs, and the encoder is 4,000 counts per revolution by default. So I've changed those parameters on the ODrive so that it can deal with the motor stator position and the encoder offset correctly. We've also got an Arduino Mega at the back that I'm just using to send some serial commands, and of course we've got a battery which is a 6-cell LiPo, so it gives us about 24 volts. The ODrive will do 48, so we're on a quarter of the power we could have, because of course if we double the voltage and we double the current, then we get 4 times the power. So this is the ODrive calibration sequence that should turn the motor either way, and that works out the motor stator offset versus the encoder position so that it can drive the motor correctly. And then it should go into closed loop control where we now have holding power. I've only calibrated it for 20 amps. We could go to 40, which will be double the current, and as I say, double the voltage, so we could get 4 times the power. But for now we've got quite a bit of holding power, and you can see that the ODrive tries to hold the position of the motor there, so it tries to fight me as I turn it. And I can't actually hold that with my hand even on 20 amps, and that's only a quarter of the power we could have. So let's do some moves and see how fast it is. So it looks pretty fast and pretty powerful. That test there was doing 1 entire revolution of the output shaft, and it seems to happen in a fraction of a second, and of course we won't need to move the dog's leg that far because that would be ridiculous, so it'd only be moved a fraction of that for for each move. We could go twice as quick as well, because of course with brushless motors the kV rating means that if we were to double the voltage it will go twice as quick, and we could go up to 48 volts on that ODrive. So it seems to have lots of power as well. You can see the torque is making it jump off the bench. This unit weighs around 1 kilogram at the moment, so I'm pretty happy with that. We could really do with putting an output lever on this to actually make the leg and see how much actual power we get, and check I definitely can't make this belt skip with the right sort of loading for what we think the dog is going to weigh. So we're going to do that next and design the next piece of the leg. I've done some more work on the leg there. The main features are the belt drive, which is the belt reduction straight from the motor onto the knee, and we also have a place here to put bearings, so we can put a rod in between the two halves of the frame, putting bearings with idlers on to get that belt tension perfect, and also means that the belt will run inside the leg and out around the knee. At the bottom of the leg, the bottom splits into two pieces so that we can get the belt in the gap there, of course, and we've also got this interchangeable foot which will allow us to put different feet on for testing. Now this design's pretty chunky still, there's still some refining to do before we get to the final design, but this is good enough for testing load. So here are all the parts printed. These are Lulzbot Morse Struder parts with the 1.2mm nozzle, so those are pretty chunky at the moment. And of course the motor fits on that one, and the encoder goes on the back again. Now I've got these normal prints that are fitted in here to get the tolerance for the bearing correct for the knee. Of course the 2020 shaft fits in here, which comes from the hip we've already built, and I already made a test piece to make sure that was nice and tight before I sized it for printing with the big nozzle. This is the bottom of the leg, which is of course split, and I screwed that back together so we've got the belt in the middle there, and the foot is actually off one of the other test dogs, and it's a Ninja Flex foot, so I thought I'd reuse that for now, and that fits nicely in there. So here's my whole test leg fitted together, and I've got all my belts in there, all my tensioners, motors and encoders. So I fitted two idlers in here to hold that belt nice and tight, which seems to be working okay. The only thing I've noticed is if I squeeze this belt, don't know if you can see it, but basically this piece of plastic is bending, and having fitted the idlers and left it there overnight, it has actually warped the plastic. So that piece is bending upwards, which is a bit of a problem. So we either need something that braces the end of this, or we need to brace against this point and this point with additional bearings to hold them apart. But for now it'll do for test. That's nice and tight and it's not going to slip anywhere. So again, there are two idlers in the top here that bring that belt in so that it's brought in nicely to come down the leg and round the knee pulley, and that's okay as well. This piece of course has got a top on, and it's also got two bolts bolted through with nuts and heads each side here, so that's stopping this thing shifting like this, so there isn't as much flex on this motor. We could still go and put something else to hold the end of the pulley though. And of course that 2020 sticks through into the thick piece here, which is the actual axle that's coming from that shoulder joint, so we could easily tap the end of this, put a 5mm bolt in and put a bearing in the end of that pulley just to help hold it and give extra tension. So that is the leg powered up. We've got 20 amps holding torque, and we're still using that 24 volt LiPo there, so that should be fine. We could go to more power. Most of the load of course is taken in the knee, but that feels kind of okay, and if I hold this piece parallel at the top, we can probably exert quite a lot of force downwards. So let's put that on a scale and see how much we're actually getting. So this is really the test to see how much load each leg will support, which means we can work out how much to build the whole robot. So if I push this down, if I put most of it just on the knee by just pushing this, we're getting over 5 kilograms. And if I hold the top parallel, yeah, nearly 10. I think we got over 9. And if I, yeah, something like 8 or 9 kilograms that we can support on each leg, which is quite good. So I've now got the leg in an even straighter pose. That means I should be able to exert more force, of course, because there's less leverage on those joints. So if I push that down, yeah, we've got 11, 12 there. 11, 12. So that should be all right. So each leg can support quite a bit of load, although we do need to refine this design. And the leg itself weighs about 3 kilograms, which is far too heavy, and we can definitely make that lighter. But you'll notice there's lots of natural compliance in these joints. They're quite springy, even though there's actually no springs in here at all. We're just back driving the motors, and the ODrive with the encoder is trying to hold the position by dumping more current on them. So that gives us natural compliance, and we can tune that in software as we did with the previous test dogs to make that leg more or less compliant, depending on what we're doing and what motions we're making. So this total leg assembly, including the shoulder and the knee and all the motors, weighs around 3 3 kilograms. The shoulder assembly is about 1 kilogram on its own, including the motor and the metal I've put in with these idlers, just over, and the rest of the leg is around 2 kilograms. Now 1.2 kilograms of that is actually just the 3D printed plastic, and the rest is down to the motor and the metal in the bolts, the bearings, and all of those other bits and pieces in there. So with 4 legs, that means our robot's going to be at least 12 kilograms just for the legs. Then we need to put the body on, and that consists of 4 hip assemblies, which are very similar to the shoulder assembly. So that's another 4 kilograms, plus a battery, that's about 700 grams. We might need 2 of those. So we're really pushing 6 kilograms, maybe up to 8 kilograms of all the electronics and frame parts and everything else in. That gives us a total weight of 20 kilograms for the whole robot. Now MIT Cheetah is about 10 kilograms, and also its reduction on its motors are 10 to 1 and mine are only 5 to 1. So that's got some considerable advantages. I really need to try and make this robot much lighter. But if we can knock some off, obviously these parts are quite chunky at the moment, and we can get rid of some of the metal like we did in miniDog 2, where we got rid of all the bearings and just had aluminium tubes and the plastic running straight on them with grease and some things like that. Then we can probably try and get that robot down to nearer 15 kilograms. And then obviously the weight on each pair of legs, when it takes 2 legs off the ground, is only about 7 or 8 kilograms per pair, which is only 4 kilograms each. And based on how much force I could apply on top of this leg with the leg bent, it looks like that should carry it. So let's have a look at a more refined design I've been just working on while the parts were printing, and then we're going to need to refine that even further. So this is what I've worked on so far. I've pretty much just taken the legs as they were and added on the body, and we've got the additional axis here for the hip. Each one of those, of course, is another belt drive from another motor, and we've got the motor mounted in the front here that drives the left-hand hip, and then in the back that drives the right-hand hip, and the back and front of the robot are the same, but it's not perfectly symmetrical. I don't think it's going to be much of an issue because it's still going to be quite well balanced. Each of these 3D prints, along with its counterpart for the front of the other hip, is about 500 grams. So there's about 2 kilograms of 3D printing there, plus the motors, plus the frame parts. Then we need to put in 6 ODrives and the electronics and a battery. So we may get to our 6 kilograms, but I think I can optimise these even further. I have done some work on the legs just by filleting off these corners, which is very nice but hasn't really removed much bulk. So we still have this big fat piece here, which is where that piece of 2020 extrusion fits in and goes all the way through to make that joint. So I think that could still go skinnier, and we could definitely bring down some bulk on the legs, then take out all the steel and use different bearings. So let's have a little chat about that now. One of the only reasons this piece is so bulky is because I wanted to make this really wide, because we've got that piece of 2020 poking in from the shoulder pivot, and I wanted to make sure we could clamp it really tight. However, in my test piece, to test for the whole size, it's actually pretty tight anyway, and that thing is only half the thickness. I haven't even put the T-nuts and bolts in here, and in this one I had an additional hole so that I could clamp through the slot here, and that would allow me to clamp down really tight with a 6mm bolt. So I think we could probably lose half of this bulk here, making it only half as thick, and that would still be just as good. Then we can move the motor in, make the whole leg a lot skinnier, and we could lose half of this here as well, and move the pulley right over, so that means the bottom of the leg could be much less chunky too. We could probably lose the steel in this joint as well by just using a plastic stub stuck on the outside of these parts and a thin wall bearing, which is pretty light, and then just getting rid of the skate bearing and the M8 studding and all the nuts. I'm not sure what to do about the idlers yet, but we could probably do a very similar thing. They may even run on bushings, depending on how fast they need to go, although I quite like the bearings, but we could probably go down to internal 6mm or 5mm ones instead of 8mm, and that will reduce the bulk of the steel, and even maybe put them on aluminium tubes. For the hip part here, I'm pretty sure we could lose all of this bulk and just have 2 parallel plates with a motor sandwiched in the middle, and then the other plate would be on the top here, which would help brace these 2 pulleys apart, as we mentioned before, probably connecting to where these idlers are if we even need them. And yes, I'm aware of the topology optimization and generative design features in Fusion 360, which will allow you to just generate the material you do need for the part based on the forces you specify. I don't think I'm quite ready for that though yet, but if you want to see Tom Sanladera's shelf brackets, you should check that video out, and that's quite a good explanation. For now, I'm just going to basically trial and error the parts, and I think I can pretty much work out what I need to do. Also, the forces on this are quite complex. It's more than just compression in one direction. We do have torsion as well, which is twist, and lots of other things to check out. So that's all for this episode. Next time I'm going to come back with a more optimised leg and hopefully get on with building sort of half of the dog or something like that and get a fair way on with a mechanical design. So that may take some time. I'm not sure if it's coming up next week or the week after, and there might be another project, but we'll see how I get on. And of course I need to order some more parts so that we can actually put that together. If you'd like to support me on Patreon or for a YouTube channel membership, then that'll be really nice. The links are in the description below, and don't forget my merchandise store. Alright, that's all for now.